Hey guys. Oh, hey guys. That's right. Hey Lily, can you go to the living room? Okay guys, sorry. Um, we are traveling into the last section, right? Last section, I hope, in chapter 9, and it's something we really already talked about. It's two-dimensional collisions. So let's go ahead and just get started. We've taken enough notes that I don't really feel like it's okay, Lily. Like we don't have to fill in all of the beginning parts, but I would always encourage you to do so because you might see something from a different perspective. If you look at Mr. McBurney's answer key, you'll notice he does things a little more differently than I do, but they both check out pretty well, and overall they're just about the same. So example 1, we have a car with a mass of 950 kilograms with a speed of 16 meters a second approaching the intersection shown in the diagram. A 1,300 kilogram minivan is traveling 21 meters per second and is heading in the same direction. The car and then a minivan collide and they stick together. Please circle that. And then I want you to write up here when they stick together that it's completely inelastic. So we are not going to be conserving we're not going to be conserving kinetic energy. Find the speed and the direction of the wrecked vehicle just after the collision, assuming external forces like friction can be ignored. All right, let's do this. So the first thing we're going to always make sure we reference is that initial momentum equals final momentum. But because we're in 2 dimensions, this gets pretty difficult. So instead of like thinking about it as overall, we're going to be thinking about it as our x momentum equaling our x momentum. So we're going to be thinking of our initial momentum in the x direction wanting to equal our final momentum in the x direction. So we're going to talk about conservation of momentum in the x direction and then conservation of momentum in the y direction. So when we have 2 dimensions, these are the 2 that you really want to focus on. Let's talk about the x direction first. Okay, so let's talk about the x direction. So we know that momentum is mass times velocity, right? So I'm just going to call this one car A, I'm going to call this one car B. They're using 1 and 2. I kind of like using A and B. It kind of helps me see my ones different than my I's at times. So we know that the mass of A, oops, made that A way too big. We know that the mass of A times the initial velocity of A in the x direction plus the mass of B times the initial velocity of B in the x direction needs to equal the mass of A times the final velocity of A in the x direction. A lot of stuff, huh? Well, I like to switch. I'm going to switch that F and the A. Who knows what's really supposed to happen, but like that. Look at that vax. The vax. Plus the mass of B times the final velocity of B in the x direction. Now let's fill these in with whatever numbers we can conjure up. It says that the mass of A is, well, how big? 950. So let's replace this with 950 for the mass of A. Now, the velocity of A in the x direction, see how it's going 16 meters per second to the right? That's great. We don't have any sine, cosine, or tangent. It's just 16 there, and it's going to the right, so it's positive. Now, let's talk about the mass of B, 1,300. See how B is only moving vertically? It's only moving up? That means it has 0 velocity in the x direction initially. Now, what I'm going to do over here is because they stick together, I hope you guys used an eraser, I'm actually not going to consider them separately because they stuck together. So what I'm going to do is it's going to be my final mass, because they're together, times my final velocity in the x direction. So if I want to do my final velocity of the x direction, all year we've been doing final velocity, which would be diagonal, cosine of my angle. Because this is the diagonal, by putting cosine of my angle, I've now changed it to my x direction. So the final mass is going to be 950 plus 1,300. So 950 plus 1,300. 950 plus 1,300, double checking, 22, yep, 2,250 for your final mass because they stuck together, times the velocity final cosine of my angle. both of which I don't know. All right, let's simplify this one more step. Let's put 950 times 16 together, and then this is gonna go away. So this side is 15,200 equals 2250 VF cosine theta. That's the x direction. So kind of like keep this little guy in your back pocket, very important. And now we're going to do the same thing for y's. Okay, so we're going to do this equation, which means mass of A, initial velocity of A in the y direction, plus mass of B times initial velocity of B in the y direction equals, now let's go ahead and not separate it this time since they're going to be stuck together. That's going to be my mass final sine of my angle. Because they're stuck together, it's going to be one total unit. We can think about it like that. So mass of A is 950. Now if you look at A, it's not going up and down, so the y direction initially is 0. Plus the mass of B, 1300, times the velocity of B is a positive 21 because it's going north or up, equals my final mass of 2250, we got that from before, sine of my angle. The last thing we're going to do is 1300 times 21, and we end up getting 27,300. Oops. And the first term, as you remember, goes star and star. Okay, so my two start equations have, oh, I missed, where'd it go, guys? Oh, did you guys see it? Right there. How many minutes? 7 minutes. I should have put, silly me. Let's rewind just a sec. I forgot my VF. Sorry. I forgot my final velocity, my diagonal sine of my angle. I'm not going to fix that. My computer battery's low. I'm not going to fix that. I'm going to leave that mistake in the video, so hopefully as you proceed through, like maybe if I make a mistake, you're like, oh, remember Miss Angel, I made that silly mistake there. But I caught it, right? That's the important thing. So VF diagonal sine of theta. You always need that diagonal if you're going to use this one. VF sine of theta. I'm going to see if I can reach my cord to charge my computer here. Oops. There we go. Look, I didn't even have to get up. Okay. Okay, so here we are. We have two really nice equations, and what you need to understand about these two equations is that we have two unknowns. We have an unknown VF, and we have an unknown theta. Unknown VF, unknown theta. Well, we have two equations, two unknowns, so we have to isolate one of our unknowns. So I'm going to go up here to my first one. I'm going to get VF by itself. So I'm going to write VF equals like this. Okay? So if I want to get VF by itself, I divide by 2250 and divide by cosine. So I start with 15,200 divided by 22, and this is just your algebra 1, algebra 2 skills coming into play here. Okay, I'm just setting them both equal to VF, and over here I get VF by itself. Let's see, I'm going to get 27,300. That's a really funny too, isn't it? 2200 or 2250. What else is moving? Sine of theta. Okay, now these two are gonna by the transitive property, if they both equal the final velocity, I can just take that one and set it equal to that one. So right here underneath my line, I'm going to be doing some algebra work. So I'm going to have 15,200 over 2250 cosine theta equals 27,300 over 2250 sine of theta. And anytime you have sine and cosine together from trig class, you probably wouldn't get them on the same side, right? Because if you have sine over cosine, you can have tangent. So I'm going to move this sine to the top up here. So I'm going to do some pretty nifty little math, okay? This guy is going to go to the other side, and he's going to go to the bottom. This guy is going to go to the other side, and he's going to go to the top. And sine is going to go over here to the top. So whatever's on the top on the left is on the, whatever, let me use my big girl words, whatever's on the numerator on the left is in the denominator on the right. Whatever's in the denominator on the left is in the numerator in the right, and then it goes back and forth for the right as well. So I'm going to rearrange everything. So I'm going to have sine of theta over cosine of theta, and remember I wanted that because I know that equals tan, equals the 27,300. He didn't move at all. Okay, who else did I move? I did not move, did I? Did not move him. I did not move 2250 here. Okay, so that takes care of that and that. This guy needs to move to the bottom. And this guy needs to move on the top. Just did a lot of algebra there. And same on top, same on bottom. Save me some stuff typing in the calculator. However, you could just multiply it. Okay, so all of this equals 1.796. Now, it seems like, okay, what's the point of doing that? Well, what I just found out is sine over cosine. And we know sine over cosine is tangent, don't we? We know sine over cosine is tangent. Okay, so sine over cosine became tan. So if I want to get my angle, which is very important, I just do the inverse of tan of 1.796. That's going to give me theta. And I got 60.89. Look how beautiful that is. So we now know this angle is 60.89, which is really great. Now, you might be like, well, that's fantastic. I thought we had to find the speed. I found the direction at least, so I can say this is direction. And I'm going to say 60.89 from positive x-axis. Why not? Okay. And now to find the actual thing, we just have to solve for VF. So I can use either one of these to solve for VF, right? I mean, I guess I could solve for like my x and my y and then use the hypotenuse, the a squared b squared, but that would be silly, right? If I have an equation for my final velocity, these two here, either one's going to give you the diagonal. So I'll just choose the top one. Plug in 60.89. Get my final velocity. Let's do this thing. You can see my calculator. Good, here we go. Answer is 1389. 13.89 meters per second is my final velocity. I'm going to do a quick check. Make sure I match Mr. McBurney's answer key that I got rid of. You know what I'll do? I'll double check into my other thing. 27,300 divided by 2250 sine, divided by, because I'm lazy, I don't want to use parentheses. Yeah, we should be good to go, man. I think we did it. I'll check as I'm talking to with Mr. McBurney's answer keys. All right. Okay, let's move on to the next problem. Two astronauts on opposite ends of a spaceship are comparing lunches. That seems smart. One has an apple, the other has an orange. They decide to trade. Astronaut 1 tosses the 0.13 kilogram apple toward astronaut 2 with a speed of 1.11 meters per second. The 0.16 kilogram orange is tossed from astronaut 2 to astronaut 1 with a speed of 1.121 meters per second. We'll have to remember to make that negative since it's going left. In fact, I'm going to make it negative right now so I have that visual. Unfortunately, the fruits collide, sending the orange off with a speed of 1.16 meters per second at an angle. Oh, so this is a diagonal. At an angle of 42 with respect to the original direction of motion. You know what I thought about just now, guys? is like if this is my positive x-axis and this is 42, I guess I could like use the angle like that to get to my orange, right? So I'm gonna like also remember that I could add 180, and that if I would just want to type it in my calculator nice and simple, that overall angle is 220. Now I'll tell you what we could do, like if we, that's for the orange. I'll tell you what else we could do, but I just kind of want to put that kind of bug in your ear. Nope, what would it be? 222, right? Yeah, 180 and then plus the 42. Okay. Find the speed in the direction of the apple, assuming that it's elastic collision. Give the apple's direction relative to the original direction of motion. We can totally do that. All right, so the main thing, one of the main things obviously in here is that it's elastic. So because it's elastic, I can say that the initial kinetic energy is definitely going to equal the final kinetic energy. So let's go ahead and write that out using like variables, and then we'll fill in our variables with everything we know. So that is 1/2 m1, I'm going to call, I'd like to use, for apple, I'd like to use A, and for orange, I'd like to use B, if you don't mind. You can use whatever you want. You can use 1 and 2. So I'm going to do 1/2 ma, mass of A, velocity initial of A squared, 1/2 mv squared, plus 1/2 mass B, velocity initial of B squared, equals 1/2 mass A, velocity final of A squared, plus 1/2 mb, velocity final of B squared. That's 1/2 mv squared, 1/2 mv squared, and then just with a whole bunch of like extra little things that I don't forget. Something remember we can do, everything has a 1/2, so I'm totally ignoring the 1/2s. All right, mass of A, let's fill in. So how big is the apple? So we're going to fill that in with 0.13 every time we see a mass A. What is the initial velocity of A? 1.11 plus, let's find the mass of B, 0.16. Let's find the velocity of B, negative 1.21. You don't have to worry about the negative because you're going to square it and it's going to go away. Mass of A again, 0.13. Now the final velocity of the apple is unknown, so we'll have to leave it like that. Plus mass of B is the orange, which was 0.16. And the final velocity of the orange is given to us, 1.16 squared. Now it's a matter of putting it in a calculator and solving. So I'm going to show you how I put this in my calculator. I need to get 1.17 to match Mr. McBurney, and I don't think we're going to have trouble getting that. Are you wanting to say hi to my students?
Oh, hi, students.
Okay, they're not here. I'm recording.
Yeah, I see this much.
Okay, very appreciated. Okay. All right, so you guys can see how I do this in one step if you want. So I do 0.13 times 1.11 squared plus 0.16 times 1.21 squared. I know the negative is going to go away. That's the left side. I'm going to need to subtract 0.16 times 1.16 squared, and I'm going to need to divide by 0.13, and I'm going to need to take the square root of that answer. All right, there it is. So we got 1.174 meters per second is the final velocity of A. Please remember that's a diagonal. Okay, because it's just important to kind of acknowledge that that's the x and the y together. If we knew the angle, which we're about to figure out, we could divide it into its x and y components and prove that the momentum's being conserved in the x and the y direction. All right, now what we're going to do is try to figure out what that angle is. So let's think about our x and y directions. Which ones are easier to kind of consider? Hopefully you're thinking about the y direction, and you might say, okay, Angeli, why am I more concerned about the y direction? Well, if you look at the y direction initially, what is the momentum of the y direction? Like, what's this guy's momentum in the y direction? Hopefully you're thinking,
Forward.
no, 0. What's this guy's momentum in the y direction? Hopefully you're thinking
Forward.
0, because it's not going up and down. So I could say I can do my conservation of momentum in the y direction initial. I can like set the initial equal to the, oopsie, forgot the final. Okay, so like let's talk about the y direction because it's a lot easier because we know that the initial momentum in the y direction is 0. I mean, I guess we could do x, it's got to be conserved, but this is way easier. Okay, so we have a total of 0 in the y direction because they're not moving up and down. So let's talk about our final momentums. Well, let's do, so we have, I'm going to write it out in variables because it's easier for me to see, okay? So mass of A, velocity final of A in the y direction. Yeah, I knew my dad was coming. He said he has something to drop off. Okay, I'm going to write this. Plus my mass of B times my final velocity of B in the y direction. We totally got this, don't worry guys. So all that means is that I can replace my mass of A with 0.13. And this right here, I can replace this with sine. So I can just do, I can do 1.174, which is my final velocity, sine of my angle. And this is for A, so that's unknown. Plus my mass of B. What's my mass of B? Okay, and now, so my mass B is referring to, what do we call B? The orange, which is, orange, orange, orange. How big is the orange? 0.16 times my final velocity of the orange. Well, we know that. The final velocity of the orange is 1.16, right here, right? But remember, that's for the diagonal. And since we're doing y's, I have to do sine of 222. Now, if you're kind of like, I would have used 42, Miss Langeli, I would not have used your 222. I would have totally forgot about that. You would have got the wrong answer if you put 42 here, unless you also change that to a negative, because you realize that it's going in the negative direction on the y-axis, and we're talking about y. So it's very, very sneaky. If you're going to do sine of 42, just make sure you use a negative because it's going down in the y direction. Or if you want to avoid that, just do it from the positive x-axis, which makes it 222. And just so you can see, like if you would have used 42, you would have got a positive. And if you use 222, you're going to avoid that and you're going to get the negative you need. So you can just keep this as a plus sign. Now, something I did want to acknowledge, and if you see I made some eraser marks, is that up here, this 1.174, this was for the final velocity of A. That's why I did not use it right here for this final velocity. I only used it for the final velocity on this one because this was for A. Now I'm going to show you guys how I do this all in one step on my calculator. So you start with the left-hand side because I'm going to get sine of theta by itself. Okay, here we go. So I'm going to start with 0 minus all of this stuff. 0.16 times 1.16 sine 222. Now I'm going to divide by the 0.13. Now I'm going to divide by the 1.174. And then that's going to be 0.8137. And that's not my answer, that's just what the sine of my angle is. So I need to do this inverse sine of that number so I can get a theta of 54.46 degrees. And that's from the positive x-axis. It's asked us to find it from its original direction of motion. Its original direction of motion was, and this is for the apple, it was going to the right, so it's referring to the positive right side of the x-axis, so I can just leave it as this degree. You can safeguard yourself and say from the positive x-axis, but not needed. Okay, so just put that degree on there. All right, let's take a look at the next one. I just looked, Mr. McMurdy did not do these last two. All the problems he does he has on his notes you can find online. So if you are interested in trying them and seeing if you get the same answer as the online books, it's simple as, you know what, I'll try to find the links and I'll include them if you want to do them. Those two took up like 27 minutes, so I think we're good with them stopping here.